Welcome to the 2010 Vetlesen Lecture Series on People and Planet, Global Environmental Change. The series is principally sponsored by the G. Vetlesen Foundation and the URI Graduate School of Oceanography. The URI Coastal Institute and the URI Honors Program are co-sponsors. My name is Steve Daunt. I'm coordinating this 4-lecture series with Art Spivak and Judith Swift. Today's speaker will be introduced by Donald DeHaze, URI Provost and Vice President of Academic Affairs. Before rising to higher levels of administration, Provost DeHaze had a long and distinguished career studying effects of environmental stress, temperature, acidification, and other familiar topics to all of us on forest ecosystems. As a scientist and an administrator dedicated to environmental stewardship, he is particularly appropriate to introduce tonight's speaker. So, Provost DeHaze, thank you for joining us.
Good evening, everyone, and thank you all for braving this difficult Rhode Island rainy, wintry night to come out and hear the speaker. I appreciate it. It is special for me to sort of get back to my roots and my passion as an environmental scientist every time I get to come to our URI lecture that deals with issues of climate change or environmental stewardship or sustainability. And it's a real pleasure tonight to have Dr. Daniel Schrag from Harvard here to talk about some of the work that he's been doing. Let me take a moment. I was really struck as I looked through Dr. Schrag's bio because almost every environmental scientist and scholar that I know brings an interdisciplinary perspective because environment is not a discipline. In order to look at almost any environmental issue or solution, one needs to bring a background, either through their own experiences or through their partners in work to address the issues of the day. I noticed Dr. Schrag has a background in political science, geochemistry, paleoclimatology. He's worked with economists, and he's worked with engineers, as well as working with scientists. He's an extraordinary scholar, and it's really a pleasure and an honor to have you on our campus. Dr. Schrag is a professor of Earth and Planetary Sciences and Environmental Engineering at Harvard, and the director of the Harvard University Center for the Environment. He has studied the physical circulation of the modern oceans, focusing on El Nino in the tropical Pacific. He has worked on theories of Pleistocene ice age cycles over the last few 100,000 years. He helped develop what's known as the snowball Earth hypothesis, proposing that a series of global glaciations between about 750 and 550 or so million years ago may have contributed to the evolution of multicellular animals. And he has also worked on the early climates of Earth and Mars nearly 4 billion years ago. His most recent work fits particularly nicely in this lecture series. You heard last fall, a year ago last fall, if you participated, a whole series of challenges to our climate, to our policy, to human health, directly or indirectly related to carbon being generated in the atmosphere. What we didn't hear too much about in that series is possible solutions. Dr. Schrag's recent research has focused on the feasibility of storing captured carbon in deep ocean sediments. I think that's what he's going to be talking about tonight. He has advocated for a large-scale effort to prepare the world to capture carbon dioxide from large point sources and store that in geologic repositories. Ladies and gentlemen, please welcome to the University of Rhode Island, Dr. Daniel Schrag.
Thank you, Provost. And thanks to Steve Daunt and Art Spivak for coordinating the series and inviting me. You've had a wonderful list of speakers here so far, and it's my honor to come share some thoughts with you tonight. What I want to do tonight is actually talk about something I call the climate-energy challenge. You know, as the Provost mentioned, I'm a geologist, geochemist by training. I have worked on the history of climate on all different timescales, but about 10 years ago, I sort of felt that it was impossible to give talks about climate change without actually talking about what to do about it. And so I started thinking myself a little bit more about energy technology, and for the last 10 years or so, I've really immersed myself in thinking about energy systems at the same time as thinking about the climate system as well. And what I want to give you is a perspective on both of those. And what I want to share with you tonight is not just we'll talk a little bit about carbon sequestration, we'll talk about a variety of energy technologies, but I want to talk about also breaking a stalemate that's going on politically in the US and a strategy towards perhaps a new energy policy for the US that might actually get us at least closer to the right direction. So I'll share some provocative thoughts. Let me start out here. I wonder if I have a pointer. Here, I do have a pointer. This is a slide that, I'm sorry it's not updated to 2010. It's a slide that shows world energy use from 1850 to 2000. Okay, so this is in exajoules per year. And what you see in green is biomass. That's basically wood, burning wood, which goes way back as an energy source. Coal was small here, but growing rapidly. The 19th century industrialization, and you see coal growing throughout the last century as well. Here's oil and gas. Nuclear, the most recent arrival. Hydro was there actually way, way back, but just so small that you can't really see it. And you notice there's no separate part for renewables. Renewables are included in hydro. Hydro is hydro plus. The reason is that in 2000, the end of this graph, renewables made up such a small amount of our world energy that it was smaller than the line dividing these fields. That's actually beginning to change. Today in the US renewables is almost 1% of total energy, which is a huge triumph. The interesting question is, what's the next 50 years? What does the next 150 years look like? And it's going to look nothing like this. It's going to look completely different. And the reason that's interesting is that in some ways this graph encapsulates the industrial history of the world. A lot of the infrastructure, a lot of the major economic development of the world was fueled by the kind of infrastructure that's required. For example, in this oil field, this is about 85 million barrels of oil a day. That's 1,000 barrels a second. The world has this incredible physical capacity to deliver energy to consumers. It's really remarkable in its scale. And the question is, how is it going to continue to do that and even grow, because many, many more people in the world want access to energy, but with very different sources without harming the environment. Now, burning all of this fossil fuel, and 85% of our energy today comes from fossil fuel, has led to this challenge. Oh, there's a slide in here that simply mentions that all of these problems, energy or climate, we think of them as environmental problems, and they tended to get shuttled in with environment, but in fact, they're major economic issues and major security issues. We go to war over oil. We make decisions about energy based on trillions of dollars of investment. This is a major, major concern at all scales. It's not just an environmental issue. It happens to also be an environmental issue. So burning all of this fossil fuel, what I'm going to do is sort of give you a quick geologist perspective of the climate issue. I know you've heard from people on this subject before, but I want to sort of give you a quick overview just to make sure that we're all on the same page. This is the graph showing the lifetime work of Dave Keeling. Dave was a scientist at Scripps Institute of Oceanography. In 1957, he started measuring atmospheric CO2, and it was about 315 parts per million. And when he died in 2005, it was about 380 parts per million. He was a bulldog of a scientist. He kept measuring this and measuring it. There are a few little gaps here where he lost funding from the government. But he was remarkable. This really documents the rise in CO2 from burning of fossil fuels. At least 80% of the reason for the rise in CO2 is fossil fuels. Land use, deforestation plays a role as well. The good news is that, in fact, the atmosphere only takes up about 60% of the CO2 we produce from burning fossil fuel. The land and the ocean actually suck up about 40%, so it gives us a bit of a cushion. There's a concern about how much that cushion is going to continue in the future, but right now, we actually don't bear the full brunt of our activities on the atmosphere. Now, we know that carbon dioxide is a greenhouse gas. In fact, we measure carbon dioxide from looking at its infrared absorption. The real question is how much warming is going to occur as we add CO2 to the atmosphere. And this, in some ways, is a terrible slide to look at this. When I see this slide of the last 50 years of atmospheric CO2, what I think about is really this slide. This is now ice core data showing the same thing, carbon dioxide in the atmosphere, but this is now the last 650,000 years of geologic time. And this is CO2 measurements measured from an ice core where you're measuring the CO2 in bubbles trapped in the ice. It's been replicated by many other cores. This is the Epica core, and this is the Vostok core. And essentially, what you see, this is this different scale now. This is 150 parts per million and 300 parts per million, and you see these fluctuations. And some of these fluctuations look very abrupt, like this one right here. The important thing to remember is the time scale. Time scale is so long here that this transition from the last glacial maximum 20,000 years ago to the Holocene 10,000 years ago took over 10,000 years. So while it seems abrupt geologically, in fact, it's all about the rate, and in fact, the rate was relatively slow. Okay? Right away, you can see that never in the last 650,000 years has carbon dioxide ever been above 300 parts per million. And I think this is the right way to think about the anthropogenic experiment. Burning all this fossil fuel has overwhelmed the atmosphere's and the ocean and land's capacity to absorb CO2, and this is the result. In 2010, we're here closing in on 390 parts per million. Now, it's been very, very steep and very, very quick. And because of the inertia in the system, because of all of the fossil fuel we depend on, we're not going cold turkey anytime soon. By the middle of the century, we will be at around 500 parts per million, which is up there at the top of the screen. The question that really is in front of us as a world society is not whether we will see climate change. The question is whether we will stop at around 500 parts per million or whether we will go towards 800 or 1,000. That's really the question that we're dealing with. So we will experience dramatic climate change. And I think the right perspective on this is just to say that atmospheric CO2 has never been higher than 300 ppm, and certainly not the close to 400 that we are today in the last 650,000 years, and certainly not as high as it will get in the middle of the century, perhaps for as long as 35 million years. So we're doing an experiment on the planet that hasn't been done for millions of years. And if you think that any of us climate scientists are smart enough to predict exactly what's going to happen, you're wrong. There is a huge amount of uncertainty here. And this is what is very frustrating as scientists to see so mangled and confused in the press, especially when there's a lot of money paying people to try to confuse the public. This is all about uncertainty. This is all about risk and uncertainty. And I think that's the right way to frame this issue. Excuse me. I don't want to do that into the microphone. So let's, as a geologist, let's quickly look at the last time we think CO2 was above 500 parts per million. This is the Eocene, a time that went from about 55 to about 36 million years ago. Actually, the time scale's changed a little. It's more like 34. We don't have direct evidence that the CO2 was higher because there was no ice cores then. In fact, there was no ice. There was no ice on Antarctica. There was no ice on Greenland, so we don't have a record directly. We have indirect measurements that we can deduce what the CO2 was, and estimates are between 500 and maybe as high as 1,500 parts per million. The Eocene climate was warm. This is a picture of what western US might have looked like. Palm trees flourished in Wyoming. Palm trees can't live where there's cold winter temperatures. Crocodiles lived way up in the Arctic, up near Ellesmere Island. Antarctica was a coniferous forest. Deep ocean temperature in the warmest part of the Eocene was about 12 degrees Celsius. Again, today it's about 1 to 2 degrees in the deep Pacific. And sea level was at least 100 meters higher than today because there was no ice anywhere on continents, and the ocean itself was warmer, which also created about 10 meters of sea level rise. Very different world. Now, it would be a horrible mistake if you went away tonight thinking that this is where we're going to be in 50 years. Because the issue is that the Earth takes time to adjust to a new boundary condition. What is fair to say, though, is that the atmosphere is being returned to a state that the Earth has not seen since the Eocene. And the question is, how long will the Earth take to adjust to that new boundary condition? And the answer is, for many parts of the Earth system, nobody really knows. We have good ideas from models. We use our best understanding of the physics and chemistry of the ocean and the atmosphere and the land. And we calibrate them as best we can on modern observations. But there will always be uncertainty because no human has ever seen 400 parts per million, much less 500. In fact, no hominid species has ever seen 400 parts per million. We're really doing an experiment that hasn't been done for a very long time. Let me calibrate you on what we're talking about when we talk about global temperature change. Often we hear about temperature changes as high as 3 to 5 degrees over the century, and that's entirely possible. The models predict temperatures up to 5 degrees warmer by the end of the century. But nobody knows what 5 degrees Celsius is globally. We don't really think about global temperature. On the left here, this is what the Northern Hemisphere looked like 18,000 years ago when ice covered most of North America. So ice was covering us here in Rhode Island, went all the way down to New York City. There was so much ice stored on land 18,000 years ago that sea level was 130 meters lower than today. It's a very different world. Here's the modern Northern Hemisphere, although there's less sea ice than this picture shows. And the difference between these two in global average temperature is 5 degrees Celsius. I think this is an important calibration here. What we're talking about is this transition that occurred over 10,000 years was quite dramatic. What we're talking about is going 5 degrees in the other direction towards warmer temperatures in the next 100 years. And it's really the rate of change that worries many scientists because it's really about the rate of adaptation. If climate change was going to occur over a few thousand years, no problem. Sea level rising, no big deal. We can move cities in 1,000 years. 100 years, it's not only a challenge for us as a human society, but it's also a challenge for natural ecosystems that can't migrate as fast and they can't keep up with the change. That's really a huge challenge here. Now, if you ask, and I know Mike Mann was here last year, so he probably talked about this a lot, but if you ask what evidence do we have that what we're seeing today, the warmest years in the last, since the instrumental records have been done, have all been in the last decade, temperatures have been rising, how do we really know that that's not just part of a natural cycle? Do we really think that this is due to the rise in CO2? And the answer is yes. In fact, we know a lot about natural variability in the Earth's climate over the last several thousand years. But if you said, what's really the nail in the coffin, I think it's the work of Lonnie Johnson. Lonnie is a phenomenal scientist. Maybe he'll come and here at some point. He is, must be around 60 years old now. He's been working for over 30 years in the tropics. He's an he takes ice cores, but he doesn't collect ice cores in intelligent places like Greenland or Antarctica. He goes to the tropics and he climbs up mountains with 6 tons of solar-powered drilling equipment and then drills ice cores. And unlike mountaineers who might go summit a peak at 25,000 feet and then come back down the next day, he goes up and stays there for 3 months at a time and then carries the ice back down. He has spent 3.5 years of his life above 18,000 feet, which is, I don't think there's anybody else in the world who's close to that. Truly a remarkable achievement. There are neurologists lined up to study this man's brain. But he's still got plenty of firepower. If you met him, you'd think he's just a very mild-mannered guy. He's a professor at Ohio State University, and he's really Indiana Jones. And what he's documented by collecting tropical ice cores is he's observed the demise of tropical ice sheets. These tropical glaciers all over the world are receding at exponentially increasing rates. And because he collects ice cores from them, he can show that this hasn't happened for thousands of years. So here, for example, is a picture of the Corricalis Glacier in Peru. This is a picture he took in 1978. This is the same location in 2002. And if you went there today, this glacier would be way back and that lake would be all dried up. So, we're talking about dramatic changes, not just in Peru. This is a picture of Kilimanjaro. He was there in 2000 and then again in 2006. But you see it in New Guinea, you see it in Tibet, you see it all around the world. The reason the equator is such a sensitive place for climatologists is that the tropical atmosphere in the equator, especially at high altitude, is very stable. There's very little variability at the equator. And so when you see tropical glaciers melting all over the world, it really has to be global. It's very difficult to explain other than a global effect. And Lonnie can prove that this hasn't happened for thousands of years. And that, to me, is incredibly powerful evidence that what we're seeing today really is attributable to the increase in greenhouse gases in the atmosphere. So To sum up, I'm just going to frame it in the way that I think is the right way to think about the climate problem. Again, we're performing an experiment at a planetary scale that hasn't been done for millions of years. No one knows exactly what's going to happen. Our best models, and the models may be very good, but they tell us that there'll be winners and losers. Many impacts will be severe, and we could talk at length tonight about all of them: droughts, heat waves, floods, storms, sea level rise, mountain snowmelt. Sometimes people say, why don't you talk about all the good things? The warmer winters in New England, you know, Cambridge has become a much more habitable place. The longer growing seasons. And there's no question there's winners and losers. The reason we don't emphasize that, I think, is not because we're just doom and gloomers. It's because we actually are thinking about this like an insurance company. The right way to think about this is a problem in risk analysis. And when you do risk analysis, you think about the most extreme impacts. You don't think about the mild ones. We insure ourselves over disastrous consequences, not over mild ones. The important point is that there's going to be surprises. No matter how much we understand about the Earth system, we will never understand enough to make perfect predictions. And so there will always be uncertainty. And let me give you a couple of examples to show that. By the way, of this list, the one that often gets least attention is mountain snowmelt. And this is one that recently in the press has gotten some attention, unfortunately, for bad reasons. But I think it's actually the one that may actually impact humans the most. This is a picture from a climate model, and I'm generally not a big fan of climate models, but this is one example of what a prediction of what water resources might look like at the end of the century under higher CO2 conditions. This is late 21st century change, and this is how much earlier the peak in snowmelt will occur. So the colors, if you look, this is the western US. For example, I used to live in California, and here in the Sierra Nevada, you're talking about numbers like 40 to 60 days earlier for the snowmelt from the Sierra Nevada. Now, like many parts of the western US, the Sierra Nevada is essentially the natural reservoir that allows California agriculture to exist. Snow falls in the wintertime and then runs out throughout the year. If you did away with that snowmelt, if that snow fell as rain, or if that snow all melted in March and April and wasn't there throughout the summer, California agriculture would be impossible. You could not build enough reservoirs, even if you dammed Yosemite Valley, to make up for the natural capacity that mountains have. So mountain snowmelt may be one of the things that is most difficult for us to adapt to as a society. And if you think California is vulnerable, you should think about Asia. The great rivers of Asia, the Ganges, the Indus, the Mekong, the Yangtze, and the Yellow, and they're all sourced from this region in the Himalayas and the Tibetan Plateau. This recently has gotten some press because the IPCC, the Intergovernmental Panel on Climate Change, mistakenly put in some sentence that somebody wrote saying that these glaciers would be gone by 2035. The correct answer is nobody has any idea when they are going to melt. The glaciers are melting. Also, the snow that falls there annually is melting earlier in the year. Truth is, nobody has any idea what's really going to happen there. But it's sort of like playing Russian roulette. This is essentially the water supply for almost 3 billion people. So this is a really big deal. So I think, unfortunately, the press has covered this terribly, focusing on, you know, how could the IPCC scientists get it wrong, as opposed to the fact that the Asian river systems are potentially incredibly vulnerable to climate change, and the fact that we don't know exactly when the disaster is going to strike doesn't actually change the fact that it's coming. I think that's the important perspective. Let me give you another example of just how conservative scientists are and why I think, in fact, we may be underestimating the problem by a serious amount. Here's a nice example. This is from the IPCC again, but this is their compilation of what sea ice is going to look like by the end of the century. I want you to focus on this upper right one here. This is July, August, September. So this is summertime sea ice in the Arctic. And you see here the Northern Hemisphere. Here's the Northwest Passage between Canada and the North Pole. These passage that Amundsen took 3 years to get through, heroic mission. That's what the prediction would be like for the end of the century from these models. And then in 2007, this is what happened. This is a picture that NASA put together showing the change in sea ice over the year from microwave images because there's not enough sunlight in the wintertime. So here you see springtime coming to the Arctic. You see the melt occurring. That's what it looked like in September of 2007. Now, this shocked even Arctic scientists who've been studying the system for a long time and had been predicting declines. The reason, it turns out, is that the aerial extent of ice is not a very good measure of what's going on this Arctic ice sheet. It's the thickness that really matters, and the ice had been getting thinner and thinner and thinner, and then the right meteorological conditions and the wind field essentially created a huge drop in the aerial extent of ice that particular year. But this is incredible. Look at this. This is the Northwest Passage. It took Amundsen 3 years to get through. You could cruise through in a 20-foot sailboat. I mean, this is nothing. The entire margin of Russia is ice-free. In fact, last year, a commercial vessel went through the fabled Northeast Passage, which is here, which never existed until this year. But now a commercial vessel actually made it through. By the way, geopolitically, opening up of the Arctic changes a lot. Panama's in real trouble. So now, again, we don't know exactly how long it's going to take for the summer sea ice to be completely gone. But now some scientists are predicting that it might happen by the middle of the century. Now, the good news is that this sea ice decline, which happened much more rapidly than most scientists expected, again, is a reminder that the Earth system may be more sensitive than the models. But the good news is that this sea ice itself doesn't change sea level because it's already floating on the ocean, and it's also very thin. The bad news is that what the sea ice really does is it essentially insulates the atmosphere from the heat that's stored in the ocean. Well, no, down here near the coast, it's warmer than going inland. And so, I mean, even the difference between here and Narragansett is substantial, probably, on some days. And what this, essentially, the Arctic ice sheet does is allows the Arctic to get very, very cold in the wintertime. If the Arctic were ice-free, you could change things dramatically, and that would be a big deal for Greenland in particular. And Greenland does matter for sea level change. So Greenland today, Greenland has about 7 meters equivalent of sea level stored on it. That means if Greenland melted completely, sea level globally would rise 7 meters, 23 feet. The good news is it's not melting that fast. This is the best estimates we have. It comes from a satellite that measures the gravity field of the Earth. So it actually looks at the change in mass on Greenland, and it's measuring, the measurements are, over the last several years, it's something like 250 cubic kilometers of ice lost per year. Now, if you think about the scale of this auditorium, 250 cubic kilometers is a lot. But the good news is the oceans are so vast that it only means it's about 0.5 millimeter of sea level rise a year, or 5 centimeters over the century. 5 centimeters over the century is not so bad, right? The question is, we've seen these dramatic changes in Greenland over the last decade. What's going to happen over the next 100 years? Is it possible that it will dramatically accelerate? And the answer is, we don't know. We had a serious glaciology conference at Harvard last year. Best glaciologists in the world gathered to talk about this issue and the issue of Antarctica, and it was shocking how crude the state of the art is. We really don't understand this. We don't even have the measurements to begin to try to constrain this problem. Let me show you how the IPCC dealt with this, just to give you a sense of, again, how conservative the scientific community is. This is the IPCC's estimate of global sea level rise over the century. These different letters here and numbers are different scenarios. They're different development scenarios that result in different emissions levels for the atmosphere, ranging from the ones over here that are relatively low emissions to the ones over here that relatively high emissions, high use of fossil fuels. And what you see, though, is that the difference isn't that great. We're talking about numbers like 20 to maybe 60 centimeters of sea level rise over the century. Okay? That's a big deal if you live right on the coast, but that's not quite as bad as some people are talking about, right? If you listen to Jim Hansen, he's saying, you know, several meters of sea level rise in the next 100 years. Why is he doing that? Well, most of the sea level rise in the IPCC report comes from these red crosses here. Red crosses are the thermal expansion of seawater. That just means that the ocean's heating up and therefore expanding, and therefore that's causing sea level rise. Here's the contribution. You can't even see it. Sorry, it's a little bleached out, but see these light blue crosses here? That's the contribution from Greenland. Every single scenario, it's the same, 5 centimeters. that number sound familiar? Essentially what the scientists are doing, you know, at the IPCC, they said, tell us how much Greenland's going to melt. Glaciologists hate to do that because they don't know the answer. So they give you the most conservative answer, which is it's going to stay the same over the century. An answer that's almost certainly wrong, right? But it is the most conservative thing to say. But in terms of communicating risk to the public, it's a terrible misservice. I think that's the really important point here. Greenland has 7 meters equivalent. West Antarctica has about 6 meters equivalent. East Antarctica, we don't even want to start talking about it, has 50 meters equivalent. Luckily, it's very, very cold. Antarctica is a nice example. At that conference I told you about at Harvard last year, glaciologists were talking about what would happen in Antarctica, and they said, you know, Antarctica will probably contribute less than 20 centimeters of sea level rise over the century unless one of the big ice shelves breaks. Now, ice shelves are very different from sea ice. This is the Ronnie ice shelf's up here, and the Ross ice shelf is down here. The Ross ice shelf is essentially land ice that has now been pushed out and is floating out over the ocean, 1,000 meters thick. It itself, because it's floating on water, it's already displacing water, so breaking off the ice shelf itself doesn't change sea level. But the role of this ice shelf is essentially to buttress, like a flying buttress in a cathedral. It's buttressing the ice that's on West and East Antarctica, holding back the glaciers. So if you lose the ice shelf, essentially, you'd have dramatic flow of ice into the Ross Sea. And you could easily see half a meter or a meter or more flow in over a century. So the glaciologists say, you know, look, Antarctica is pretty stable at the 20 centimeter level unless the Ross ice shelf goes. So you sort of ask the question, well, do we know much about the Ross ice shelf? Turns out we know something about how ice shelves break off from watching ice shelves break off here on the Antarctic Peninsula. And ice shelves break because of warm water being 1 or 2 degrees Celsius, as opposed to the water that's normally under the ice shelf, which is -2 degrees, the freezing point of seawater. Just a little bit warmer, water that's coming from maybe 1,000 meters deep, that upwells and gets over the Antarctic shelf at about 600 meters, flows under the ice shelf, and when that happens, there's a cycle that forms, and ultimately that ice shelf is rapidly deteriorated. That's what happened to some of the ice shelves on the Antarctic Peninsula. So the real question is, it's actually not a glaciological question, it's an oceanographic question. What's happening at the intermediate depths between 1,000 meters and 600 meters near the Ross Sea around the edge of the Antarctic shelf? And you say, well, the only measurements we actually have of the temperature down there come from thermometers strapped to seals. Now, nothing against the seals or the biologists who put the thermometers on them. It's a great project, but in this day and age of modern oceanography, frankly, we can do better, right? But you have to understand, we're truly flying blind on this one. We don't know. We really don't know whether the Ross ice shelf is melting or not, or when it will. We don't understand the system. So the honest answer is, we don't understand it. And we're rolling the dice here. So I think the important perspective here is that scientists tend to be very conservative. Our culture believes in 95% confidence intervals. We don't like to be wrong. We don't like to speculate. And this means that scientific assessments tend to ignore or de-emphasize highly uncertain issues. And then when we hand them over to economists and policymakers, they're treated often as high consequence, low probability events. Because we like to believe that these horrible things that might hopefully never happen are low probability. In fact, they're unknown probability. We really don't know. They could be high probability. We just don't know. I think that's a very important perspective. Okay, I want to switch now and start talking very briefly about adaptation and mitigation. As I've argued before, substantial climate change is unavoidable. We will see 500 ppm. I suspect we'll see 600 ppm CO2. The question is, will we avoid 800 ppm CO2? And I think that point is important because what that means is adaptation is essential because climate change will happen. The question is, and by the way, it's not cheap. Here's an example. This is the Thames Barrier in London. So this is, cost about £1 billion when it was built. It would cost 10 times that today. And they're talking about building another because this was inadequate, has been so far, they think, potentially inadequate to protect London against the future. It was built to protect London from flooding in the Thames because it's a tidal river. And of course, the Netherlands is a place where they know a lot about protecting themselves from the ocean. Much of their land is actually below sea level. And so this is an example of the kind of investments that the Netherlands has made in dikes to protect themselves from the ocean. And then this is what we did in New Orleans. And it would be funny if this actually weren't true. Nothing against the Army Corps of Engineers, but as a society, we encourage people to live in harm's way and built totally inadequate support systems to let people live below sea level. And we were very lucky that Katrina missed New Orleans. And remember, Katrina hit Mississippi. If Katrina had actually made a direct hit on New Orleans, the city would have been flooded in about 10 minutes instead of over 2 days. There were 400,000 people still in the metropolitan area, stuck there during the storm. We could have easily lost 100,000 lives. We were very lucky that we only lost about 3,000. So the important point, though, is that without mitigation, adaptation ultimately is impossible, right? No matter how many seawalls we build, or no matter how much reinforcement, the scale of the Earth system is so large. The amount of ice on Antarctica is so great, and that's just one of the many impacts of climate change, that fundamentally we have to solve the problem. I think the time scale is important here, too. This shows different scenarios of CO2 emissions, and this shows what those emissions, in terms of billions of tons of carbon a year, would do to the concentration of CO2 in the atmosphere. And you see that in fact, the range is great, 500 to maybe 900 parts per million, but it's not that great, right? Fundamentally, and that's because the carbon dioxide lasts a long time in the atmosphere. This is a little bit of a complicated figure, but I wanted to show it anyway. It's a nice paper that my colleague at Chicago, David Archer, wrote recently. And it reminds us of something very important. The timescales of this system are very, very long. What this shows here, and the scales are different, this is 2000 to 3000 AD, and it shows two different possible trajectories. This one here, burning a total of 1,000 billion tons of carbon and fossil fuels. That's about the trajectory that we would be on if we dramatically reduced our emissions today. So that's about the very best we could possibly hope for, and we probably couldn't even achieve that. And this one, 5,000 billion tons of carbon, that would be if we essentially burned all the coal in the world. Okay, we're probably not going to achieve that much, or at least hopefully we're not either. Okay, so we're luckily going to be somewhere in between, hopefully towards the gray curve. What this shows is running this through a model of carbon in the ocean and atmosphere and allowing the ocean to take up carbon. This is what the carbon in the atmosphere does, and this is now a different time scale. This is 2000 AD again, and this is now 12,000 AD. What you see is that it has a very long tail. That is, if we peaked at around 500, 550 parts per million, we would still be at 400 parts per million 10,000 years from now. We're not at 400 yet. So those ice sheets are in trouble. If they're melting today, and we've allowed 400 ppm to persist for 10,000 years, we've got a problem. Now, of course, if we burned all the coal, we'd get up to, maybe 1,800 parts per million, and we might stabilize above 1,000 parts per million, again, for 10,000 years. 20% or so of the CO2 we put in the atmosphere will be there for 10,000 years. So this problem has a very long tail that we're not used to thinking about politically. But as an earth scientist, it's important to communicate that. So what that means is this is a problem with a lot of inertia. There's long residence time of carbon in the ocean atmosphere. There's the large thermal inertia of oceans and glaciers. Once you start melting them, you can't just freeze them again. And then there's the long lifetimes of energy infrastructure. So my colleague John Holdren, who's now President Obama's science advisor, likes to say, we're not driving a sports car, we're driving a supertanker. And it's very hard to slow down, it's hard to steer, and so when you see a shoal up ahead, you can't just wait to decide whether or not it's indeed a shoal. You have to be cautious and actually throw it in reverse. Unfortunately, that's not what we do in the policy realm. It's very hard to deal with this kind of problem. I want to make a quick comment about something that's been in the news a lot recently, also made famous by the new Freakonomics book, which really did a terrible job explaining this issue. It's something called geoengineering, which is a term that I've stopped using because geoengineering refers to all of these things. It refers to iron fertilization of the sea, encouraged by your former dean of the Graduate School of Oceanography, Margaret Linen. growing trees, genetically engineering crops. Some people call carbon sequestration geoengineering, all sorts of different things. What I think is a very different category is a direct intervention in the solar radiation budget, what we call solar radiation management, or what I sometimes call climate engineering. And the reason that's different, that's these things here, giant reflectors in orbit, cloud seeding, aerosols in the stratosphere. They actually have an immediate impact on the Earth's radiation budget, and that means they cool the Earth right away, on the time scale that the sun warms the Earth. So it's a very big, instantaneous effect. The good news is cloud seeding is too transient, we can't control it well enough, and reflectors in orbit are so expensive that they're never going to happen. We don't even have the rockets to put them up there. But aerosols in the stratosphere is a very serious suggestion. This is essentially artificial volcanoes. It was originally pioneered or championed by Edward Teller. Some of you know Edward Teller. That should send a little bit of fear in you. He was one of the proponents of the hydrogen bomb. But it's a very serious suggestion. The idea is essentially to mimic what a volcano does to climate by essentially putting up aerosols in the stratosphere that would reflect sunlight. Now, reflecting sunlight doesn't cancel out directly the absorption of heat by greenhouse gases. So it's not a perfect cancellation. Okay, there are impacts. The diurnal cycle is affected, the seasonal cycle is affected, ecological systems are affected. So it's not a perfect fix. But it would keep the Earth cool, potentially, and keep the most disastrous effects from happening. At least that's what our models suggest. We had a conference on this almost 2.5 years ago now at Harvard in the early days of thinking about this. And these are some of the questions that we asked at this workshop. How do we do it? What does it do to the climate system? How good is this cancellation? What might go wrong? Again, we're talking about something that would be protecting every living thing on the Earth. And so you have an obligation to make sure you don't screw it up. Does it postpone the need to reduce emissions? And more importantly, politically, will it postpone the reduction of emissions because people think the problem isn't severe anymore? Who controls it? And this is a very big issue because remember, it turns out the real driving force for this and the argument that Freakonomics made, which was a horribly simplistic one, is it's cheap. It's cheap. It's incredibly cheap. And therefore, we should do it. So we're talking about China and India. You could add Brazil and Indonesia. One of the problems, by the way, I should note, is that national carbon emissions, for example, Saudi Arabia, which is very high per capita emissions, a lot of that is actually for export, right? It's that the oil industry is very intensive in terms of CO2 production, and that oil is for consumption in other places. And so national emissions, the way you define them, doesn't really deal with trade, and for certain countries, trade is very important. In Europe, for example, some countries have just exported all their heavy industry, but they still benefit from those CO2 emissions even though they're happening elsewhere in the world. Okay, there are really only 3 ways to reduce emissions. And there's one thing I want you to take away tonight, it's that you need all 3 of these ways. And you can quantitatively look at this problem and convince yourself that we know that we're going to need to do all 3 of these things. We don't yet know exactly how much. All of these are going to be at least 10% of the solution. We don't know whether one of them is going to be 50% and the other 2 are a quarter, or whether they're each a third. That's what we have to find out. The first is essentially using less energy. Sometimes people talk about it as conservation. I think of conservation as putting on a sweater so that you can turn your thermostat down. Efficiency would be putting more insulation in the walls so you actually don't waste as much energy. Whichever it is, it ends up resulting in using less energy, and that's certainly an important component. For the US, it's probably one of the biggest. We can use non-fossil fuel energy, which means renewables and nuclear, and then we can use fossil fuel energy and capture the carbon and store it underground. And it's the last one that often makes people think twice because it sounds a little scary. The reality is we use 85% of our energy, get 85% of our energy from fossil fuel, and we're not going to zero anytime soon. So we absolutely need a technology that will allow us to continue to use abundant, inexpensive fossil fuels, in particular coal, and actually not bear the brunt of the impact on the atmosphere. Let me give you some perspective on why carbon capture and storage is such an important technology. In 2005, 150 stationary sources emitted as much CO2 as the global car fleet. That's actually good news. That's a tiny number of point sources. The largest 1,000 stationary sources accounted for about 30% of global emissions, and about half of them were in the US and China. And fewer than 8,000 stationary sources are roughly responsible for 50% CO2 emissions. That's actually not so many. If we could actually capture the CO2 and store it from those sources, we could take a huge chunk out of this problem. So it's a very attractive technology if it can be done safely. It turns out we've been actually injecting CO2 for 40 years underground to enhance oil recovery. So the oil industry knows a lot about CO2, about piping it around. Kinder Morgan makes a lot of money selling carbon dioxide to oil companies to enhance the oil recovery. The question is, can we store it for long enough so that if it leaks out very, very slowly, it won't impact the carbon in a dramatic way? There are a number of commercial scale experiments going on around the world. The one that I like the best is the Sleipner project in Norway. This is in the ocean. And one of the reasons to do it offshore initially is because it's in nobody's backyard. People are more comfortable with it if it's far away, at least initially. Ultimately, carbon sequestration is going to have to happen in lots of places, but initially doing it offshore, I think, is going to meet the least political resistance, and it's important to demonstrate that it's feasible. In Sleipner, they've been injecting 1 million tons a year since 1996. I should make a note about this in New England. I've actually been working on a project in New Jersey, building a 700 megawatt coal plant that's going to capture 90% of the CO2 and inject it 70 miles offshore, right about here in New Jersey, offshore, 70 miles offshore in the Outer Continental Shelf. It turns out that the geology from Long Island south to Georgia is probably the best in the world for storing CO2. The reason geologically is that this is just a geological cross-section. Just showing here the lower Cretaceous strata, which are mostly composed of very permeable sandstones, perfect reservoir rocks. And the upper Cretaceous and Tertiary, the upper part of the sediment column, probably 2,000 meters or so, is impermeable mud, clay. And so it's the perfect geology for storing CO2. It's the safest place in the world to put it. And the good news is, for Massachusetts and Rhode Island, this region here is, about 100 miles away. So this is actually a very feasible place. Right now, Rhode Island doesn't really produce its own baseload electricity. They buy it from out of state. But if you ever wanted to, or if Massachusetts decides to build more coal plants and sequester CO2, this is where you're going to put the CO2. The reason the geology up here is no good is because the glaciers scraped away all the tertiary clay, and so there's very little thin clay covering those sandstones. So the geology doesn't work. But south of Long Island, it's fabulous. Okay. As far as reducing energy, let's remember that economics matters. We have this desire in the US to decarbonize our energy system and get more efficient, but keep prices low. And that makes no sense. Ultimately, we need to have higher energy prices. That's the only way we're going to solve this. But politically, that's a tough nut to crack. Right? This is a graph showing an estimate of high efficiency or low efficiency by country and the price of electricity per kilowatt hour. And you see it's not a perfect correlation, but it's pretty good. Economics works. Right? When something is more expensive, people are a little more careful wasting it. Surprise, surprise. Here's an important graph, though, because it shows that it's not just the price, it's also policy. Policy matters. This is the United States electricity consumption per capita. Here's Western Europe in green, and this is California in the middle. California, starting in the 70s, did something remarkable. With Governor Jerry Brown, they implemented a series of policies that included home building codes, standards on air conditioners and various appliances to mandate that they were particularly energy efficient, not just Energy Star, but really strict codes on what you could buy. And as a result, they used 40% less electricity than the rest of the US per capita. That's electricity, it's not heating. For example, Seattle, which has a much milder climate relative to Sacramento, which is really hot and nasty in the summer, Sacramento uses half as much electricity per capita as Seattle. Seattle has a lot of cheap hydroelectric power, and they waste it. So that's sort of a nice story. The good news is the US, in theory, could cut its electricity use dramatically if there were price signals were there to help, and the policies were right. Now, the other good news, and this is kind of a double-edged sword, this is just a graph showing the number of coal plants that were built in terms of total capacity over time, and you see that there were a lot of plants built in the US between the 50s and the 80s. But for the last 30 years, we have built almost nothing in the US. We have neglected our infrastructure, our energy infrastructure in particular. We haven't built refineries, we haven't built many pipelines, we haven't built gas, we haven't built many gas plants, we haven't built many coal plants. We've neglected our infrastructure, and as a result, our infrastructure is very old. Now, that's going to get expensive because we've essentially postponed that investment, and therefore we're going to have to do more of it coming up. The good news is we're going to have to do it anyway. We're going to have to make new investments in energy infrastructure anyway because a lot of these plants are really old. 20% of the electricity in the US comes from nuclear power, and those nuclear plants will be decommissioned. They have to be because they're not allowed to run, they're not safe to run. They've already been the age has been extended, but in another 20 or 30 years, almost all of the nuclear plants in the US will be decommissioned. So we have to build new capacity, and the question is, what are we going to build? This is a graph just showing nameplate capacity by fuel type: coal, gas, nuclear, and hydro. The wind and a little bit of diesel fuel doesn't even count so much. And you can see the spread, and there's a huge amount of geographic spread. I'm sorry, the boundaries between the states are a little blurry here, but if your geography is good, you can figure out where this is. You know, you contrast a state like Wyoming, which is the largest coal producer in the US, 93% of its capacity is coal. You know, here's Rhode Island, 100% gas capacity. This is actually how much electricity gets generated by those fuel types. Again, a lot of your electricity you buy from other states, but you see, you know, the mix here, 94% of the electricity in Wyoming is from coal, 1% in California, 58% from gas, 16% from nuclear, 12% from hydro. So there's a huge spatial variation, and that means there's winners and losers. And so figuring out how to do this in the US is a very complicated thing. What is it going to cost? A reasonable estimate of what is required to get to a low-carbon economy is something like 1% to 2% of GDP. And that's a very crude number, but it's important to think about how big that number is. It's a lot of money. It's about $150 to $300 billion a year. But when you actually think about what we spend money in the federal budget on, it's not an obscene number. It's a large number. Small compared to Iraq, right? We have actually done far bigger things before. This is tiny compared to the kind of investment in infrastructure we did in World War II. So if we actually got serious about this, we could do this, and in theory, it would actually involve some economic stimulus as well. We have another problem that we're dealing with as well, which is oil, which is really the king of our energy system, is becoming a challenge. As I said, we use 85 million barrels of oil a day in the world. This just shows crude oil. Natural gas liquids adds it up to about 85. And you can see that basically it's plateaued in the last several years. There's a concern that we've already reached what's called peak oil. Peak oil doesn't mean we're running out of oil. It means that we may peak in total production of oil. We'll still continue to produce it, but it may decline in total amount. This is a history of the price of oil, and you see this was the price shock where it hit actually, there's some averaging here, but it actually went up to above $140 a barrel. And the real remarkable untold story of the recession. You know, everybody talks about how cheap natural gas has been. The real amazing story is that oil has continued to be expensive during a recession. Oil at $70 or $80, historically, that's an incredibly high price for oil during a recession. And now China and India are starting to recover and are growing at 10% a year. What do you think that's going to do to the price of oil? So in some ways, that's good news and bad news. The good news is the high price for oil is probably faster than any climate legislation going to drive a quest for lower carbon alternatives, assuming they're lower carbon. But we're going to start seeing transportation alternatives because we're not going to be able to afford to pay $200 a barrel oil. It's just going to break the back of the US economy. Let me skip some of this. I should, one quick note about oil. It's that fields all over the world are declining, but one thing that nobody pays attention to is what's been going on in Mexico. This is the Cantarell field in Mexico, showing a precipitous decline in production. And Mexico's in big trouble. 60% of the revenues of the national government come from Pemex, the state oil company. And in the next 10 years, Mexico will become a net oil importer. That profoundly changes the economics of Mexico. If you think crime is a big issue in Mexico today, wait 10 years. There's a disaster brewing across the border, and it will be very interesting to see how that works out. I want to sort of sum this up now and talk about this. This is a graph that's been shown a lot. It's from a McKinsey study, and McKinsey's great at marketing their work. This, maybe people have seen this before. It's an estimated global greenhouse gas abatement cost curve beyond business as usual. So it's sort of asking how much in dollars per ton different technologies will cost. And they like to say, well, look at everything on the left side. That's negative cost. It saves money if we did it. Of course, for a lot of investments in energy efficiency, and you have to think about how long the time scale of payback is, but they actually result in a negative cost. You know, using, increasing the efficiency of motor systems, for example, or insulation retrofit, or various other technologies. The numbers here are a little shaky. This is sort of estimated for 2030, and anything they estimate is what the cost will be 20 years from now. You should know that we have no idea what the cost of some of these things is going to be. The other important thing is each of these has a supply curve. That is, how much of it could actually be supplied at that price. And you don't get a sense of that here. For example, carbon capture and storage is something at a huge scale of billions of tons of carbon, whereas some of these things like degraded land restoration is in the million tons of carbon, and so these are mismatched. The truth is, we really have no idea what these things are going to cost. These guys are very optimistic about solar photovoltaics. Right now, photovoltaics are incredibly expensive compared to carbon capture and storage. Maybe 20 years from now, they'll be cheaper, but we don't know that to be true yet. There's a lot of hope that that will happen. I think the bottom line from any kind of exercise in trying to estimate costs is that there's too much money at stake here. We're talking about trillions of dollars of investment to actually get it wrong. Picking a technology like solar photovoltaics could cost the US economy and the world economy trillions of dollars because it's just too expensive. And that money is real money when it comes to human prosperity, helping care for the world's poor, for example, or all the other things that we actually do to care about the world. So many people have argued that we need a price on carbon to let the market actually figure out what the right technologies are, let people compete. And I agree with that, and certainly a price around $30 a ton is a great place to start. There's been an attempt in Congress to try to do this, and that's the Waxman Markey bill. Ed Markey, our congressman from Massachusetts, back when we actually used to have a completely Democratic congressional delegation. Basically, it's a complex cap and trade system, much more complicated than the RGGI system that is in force here that only takes care of the electricity sector. It basically buys political support with all sorts of allowances and loopholes. It's a horrible congressional bill. And many environmentalists just hold their nose and say, well, it's better than nothing. There's enormous emphasis on carbon offsets, for example, to get votes from the Midwest. They're promising the farmers will get paid to take up carbon in their farms, regardless of whether there's any scientific evidence that it does anything. So it's a problem. It's not a great bill, but it's a start. And there's one excellent argument that I've heard made in favor of it, and that is that China, which is now the biggest emitter of CO2, wants to see the US lead. They want to see the US go first, and this at least is something to show the US is serious, and then that will bring China to the table. And that is a good argument. A very good argument against is that the Waxman Markey bill eliminates EPA regulatory authority under the Clean Air Act. That essentially is being used right now as a sort of gun to the head of Congress to do something. If you eliminate that authority, it's not clear that Congress will do anything to make this bill better in the future. And it may be too big a giveaway for a bad bill. Whatever we think of this, it's dead right now. Since the Waxman Markey bill, a lot of things have happened. Public concern about climate change has plummeted. Part of the reason for that, last year, environmental groups have been outspent by the fossil fuel lobby. Lobbying on this issue, $300 million was spent by the fossil fuel industry compared to $13 million. We're talking about some of the most powerful, largest businesses in the world who are spending a huge amount of money to stop this from happening. Massachusetts, of course, has also become purple. Public trust in markets and Wall Street has plummeted. That means the whole idea of cap and trade scares people. They don't want to create another market for Wall Street to screw up. And we know the Supreme Court has allowed corporations even more political free speech, which makes the passage of something like this even more difficult. The other thing that's happened in the US is there's this huge enthusiasm about shale gas, about the production of natural gas from very tight shale formations. Evidence of that, ExxonMobil brought XTO Energy recently for $31 billion. So suddenly we're talking about a growth in production of natural gas. Worldwide, natural gas has been on the rise. And in the US, this is a projection of what it's going to be in the future. The EIA, the Energy Information Agency, is projecting an increase in gas production, most of it coming from the increase in shale gas, this dark blue part. US turns out to have a lot of shale gas, and this is very exciting. The reason shale gas can actually do a lot to reduce emissions is because it competes with coal for electricity, and not only is the carbon content half as much per BTU, per energy, but it also, the gas plants are more efficient, so it's about a third of the emissions of coal per electricity produced. So it's a big drop if you replace coal with gas. The problem is the amount of coal we use is so huge. It's responsible for 50% of our electricity generation. We're not going to back out all of the coal anytime soon. We're never probably going to be able to get rid of coal altogether. But here's the interesting thing, and this is what I've been working on recently. The geopolitics of gas is very interesting. This is a perspective of gas production in the US in conventional fields, and it's really concentrated in a few areas, but gas has never been politically powerful because it's been really owned by oil companies as a side business. That's changing. Here's offshore gas production. This is where shale gas is in the lower 48, and look at its geographic spread. It actually matches up pretty well with coal. Now, anybody who knows about Congress knows that the power of the coal industry in Congress is enormous. They have old connections with a lot of senators. It's claimed that the coal lobby has 40 votes in the Senate anytime they want. That makes it very tough to pass a climate bill. What is, I think, an interesting path forward for the US is potentially an oil and gas friendly climate bill. And I think we're beginning to see the beginnings of this in the Senate. It should make all of us a little uneasy because remember, we're talking about buddying up to ExxonMobil, the largest publicly traded company in the world, very powerful. But the question is, why not use the economic power of the oil and gas industry to overcome the political power of the coal industry? The recognition is that with a price on carbon and a climate bill, the big winner economically is going to be ExxonMobil. They're going to sell gas. They're going to replace coal with gas because gas is going to compete better with coal. It's kind of counterintuitive, but in fact, I think this is a very interesting possibility to scramble the politics of this issue that we're going to see over the next several years. We're going to start seeing the oil companies switch sides and actually start fighting the coal lobby in an interesting way. Again, as a geologist, I say, again, serious policy action on climate change is inevitable. It's a question of when, not whether. Now, unfortunately, by the time people get scared enough about climate change to demand action, it may be too late. So I'm hoping that it'll be sooner rather than later, but eventually the climate impacts are going to start to catch up with us. I actually believe in the next few years, I suspect it's not going to happen this year before the elections, but I believe a bipartisan climate energy bill is a real possibility structured around gas and nuclear with a price on carbon. I think we have to remember in the end, though, that mitigation of climate change requires massive capital investment. We're talking about the largest build-out of infrastructure that we've seen since World War II. So there's huge economic opportunity for the US in this. This is actually a challenge for environmental groups, though, because environmental groups have been essentially for the last 40 years set up to oppose development. And climate change is all about development. So it's a very interesting challenge for those of us who care about the environment. It's going to involve a lot of hard choices. We're seeing this with Cape Wind in Massachusetts. There are people who think it spoils the natural landscape of the ocean, it's a very tough trade-off because climate change is going to do a number on the ocean environment as well. So I'll stop there and be happy to take any questions on any of this. Thanks very much.
Hi, I'm Nicole Rohr, and you gave a
Nicole
lot of...
Rourke?
Rohr.
Rohr.
You gave a lot of great information about kind of what the general climate problem is and some great solutions, but how I think that we're missing an important link about how to actually convince everyone that there's a problem to begin with. Seems there's a lot of resistance in certain areas, obviously not in the scientific community where we kind of surround ourselves, but with the general public, that there's not a global climate change problem, that this is just a natural cycle. How do we overcome that and incorporate that so that we can then have these solutions in Congress that are supported by representatives and senators?
Sure. That's a very good question. I think the answer is, first of all, that there are a few heroes like Lonnie Johnson who have really done such beautiful pieces of science that are so, the imagery, and they're so compelling that people actually understand it at a very basic level. We have to remember, though, and so I think there's all sorts of things to do to help communicate this to people. Teaching in schools, teaching in everything from elementary schools to high schools, communicating with friends, talking with communities in all different ways. I taught a graduate course last year with 35 graduate students, and one of them, for her term paper project, went home to her church and actually gave a sermon about climate change to her local church at home. Lots and lots of possibilities. That being said, we've got to remember that there is a lot of money being spent to try to convince people that this is not a problem, because there's a lot of vested interest in continuing to burn very cheap coal and make a lot of money off of it. This is pretty heinous. I mean, this is really like the tobacco battle, but maybe even worse. And it's a lot of the same people they've hired. You know, I was in Washington a few years ago testifying before Congress when Senator Inhofe still ran the Senate Environment and Public Works Committee. And he had hired as his communications director a guy named Mark Morano. And I questioned something that Senator Inhofe said about the Kyoto Protocol. And Mark Morano issued a press statement right after our session where I was the leading subject, that essentially I agreed that Kyoto would make no difference, which was a total twisting of my words. It was absolutely, you know, taking things completely out of context. I later learned that this guy used to work for Rush Limbaugh, but between that, he was the guy that broke the Swift boat story on John Kerry. I mean, these are not coincidences, right? These are people who were paid to distort the truth. And that's one of the reasons why I've gotten interested in saying, okay, how can we actually change the politics of this and the power of this? Because fundamentally, I would love it if environmental groups and scientists could actually beat the entire fossil fuel industry. I'm beginning to think, and I had hoped that that might happen. I've got to say, it looks pretty dark right now in the US, doesn't it? And for this issue. And I think the honest answer is we need to scramble the politics of this and get some money on the other side. And we have to look to the companies that are going to win in a world where we take action on climate change to actually take the political lead in pushing for it, which for a variety of reasons they haven't done until now.
My name is Paul Baudette. It was a two-part question. One of the key greenhouse gases you didn't mention is the growth of methane, which is 20 to 25 times more potent than CO2. And how, from your knowledge, how can we address capturing that when it is everywhere being released? And then secondly, could you speak, since you talked about the shale gas, some of the implications on the Marcellus shale beds and what development of that area would do to some of the trade-offs that the environmental groups are going to have to look at. In particular, water impacts, 7 million people in New York City on through to Pennsylvania and Ohio in their water streams.
Sure. So let's talk about that. As far as the first question, wait, remind me what, the methane in the atmosphere. Methane is, when you compare methane with CO2, it's a little difficult because methane is a more powerful greenhouse gas, but it has a much shorter lifetime in the atmosphere, only about 10 years. So that 25 times more powerful number is when you integrate over 100 years. If you integrate over 500 years, it's only 8 times more powerful. So it depends on the time scale over which you look. Currently, methane is responsible for 15 to 20% of the total greenhouse gas effect. CO2 is about 70%. The main anthropogenic sources are actually the same as natural sources or wetlands. It's just the anthropogenic sources are things like rice paddies. Cows are a minor issue, not insignificant. Landfills and natural gas production, leakage from pipelines and things like that. But rice paddies are the biggest by far. Some people have argued that dealing with methane is a very good way to deal with greenhouse gases in a hurry because it has such a powerful effect. You wouldn't actually try to capture it from the atmosphere. It's less than 2 parts per million in the atmosphere, so it's very low concentration in the atmosphere. It's just very powerful. But you could capture it. We could do a much better job of, for example, capturing methane from landfills and using that gas, et cetera. So there are lots of programs out there, and we do that a lot. But fundamentally, I think the reason I think that it's not a great place to start, and the reason I don't talk about it very much, is because it's very difficult to think that you're going to stop rice production. You really can't have rice production without producing methane, and so it's really difficult to think about how you actually cut that out. A much more interesting trace gas to think about is actually N2O, which lasts for a very long time in the atmosphere. It's very low abundance, but it's really enhanced by certain farming practices where we over-fertilize. And one possibility is to change the way we use fertilizer to reduce the impact of N2O. But again, all of those are small compared to carbon. You know, the way I think about it is this. There are lots of greenhouse gases that we could worry about, but if we don't solve the carbon and fossil fuel problem, we won't solve the problem. And so that's really where we need to focus our attention. That would be my argument. As far as the impact of the shale, whether it's the Marcellus Shale in New York and Pennsylvania and Ohio and around there, or whether it's other places, recently there have been a lot of questions about the drilling technologies and whether or not that might potentially contaminate groundwater. The best work that's been done so far, and we need more transparency, but the EPA just came out with a good analysis saying that there's no evidence at all that, in fact, the shale gas production has really impacted water quality at all. These shale beds are, deep. They're a couple thousand feet or more, well below any kind of drinking water aquifer. Now, certainly it's possible that a bad driller and a bad accident could screw something up, but that can happen in a coal mine or that can happen anywhere. The irony is that recent evidence is that it's actually the coal industry that's been funding the media hype about how shale gas is contaminating water supply, which is sort of ironic given if you know what happens in West Virginia to the water supply and rivers there, streams. I think the best answer was shale gas. I was very concerned about this as a geochemist, and I think the best evidence is that shale gas is not a big deal, that the hydrofracking is not a problem because it's happening so much deeper than the level of the aquifers. And so none of the hydrologists that I've spoken with about this issue think that it's a serious issue. But there's a lot of money being spent right now pushing this issue, and I think, like any new technology, we should be careful. We should have good environmental regulation, and we should have good transparency and reporting. But I don't think it's likely to be a big problem. Does that answer your question?
I suggest we only take one more question, and then if anyone, and then people can go. If anyone has any remaining questions.
Noel Rowe, is carbon sequestration technology possible, or what is your take on it?
Well, as I said, it's being done in the North Sea at 1 million tons a year since 1996. We estimate the capacity off of New Jersey, just in that region off New Jersey, to be several hundred billion tons of CO2, far more than we could ever produce in the Northeast.
And how does it work then, I guess?
Essentially, when you pump the CO2...
How does it get to 100 miles offshore or whatever?
So you build a pipeline, and you pump the CO2 under pressure down. Again, this is kind of low-tech for the oil industry. And you injected it, in this place, it would be 2,500 meters below the sea surface in about 100 meters of water. At those pressures and temperatures, the CO2 has a density of about 0.85 grams per cubic centimeter. So it's almost the density of water. So it's much less mobile. It's not a gas that's moving around. It's not a liquid either. It's called supercritical, but it's quite dense. And the nice thing about the East Coast is it's a passive margin. There aren't a lot of faults and fractures, and the mud in the upper 1,000 meters is so soft that even if there were fractures and faults, they'd heal themselves. So there's really no way for that CO2 to get out. It'll be there for millions of years. You'd have to pump it out. Eventually, that CO2 would dissolve in the pore water in the spaces, and then it just becomes seltzer, essentially.
Please join me in thanking